In this video, we'll look at capacitors in parallel and capacitors in series. So in parallel, what that means is that the two capacitors are across from each other. And there can be more than two. Let's just start off with two. And it turns out that the voltage is constant. So let's say we have this hooked up to a 12-volt battery. What that means in terms of a circuit is it would be 12 volts over here, and then it drops to 0 when it comes back to the battery. You could imagine we just put a battery down here at the bottom, like a car battery. That means that the voltage here, the drop, is 12 volts. The voltage drops 12 volts there as well, no matter which way the electrons go. You can almost think about the electrons kind of like they're water, where they flow this way and they flow that way. So if we look at QVC, Q equals C times V or V times C, but the voltage drop is the same. So it's C1, capacitance 1 times the voltage, plus capacitance 2 times the voltage. So the way that works out and the way the math works out is we could have what's called the equivalence capacitance. And for parallel, it's easy. For parallel, all you simply do is add them. C equivalent equals C1 plus C2, etc. for as many as you have. You say, well, why is this? Because what it works out to is it's like using a larger plate. So you could almost imagine instead of two split plates here, we could have one big one. Now in series, the charge is constant. So if we have, let's just say 3. If we have 3 positive charges, 3 negative charges. Then for this plate, in series, they're just lined up. Like if you watch a television series, you watch episode 1, you watch episode 2, and then you watch episode 3, and before you know it, you're all the way through Tiger King or whatever you like. Now the reason these charges have to be equal, if you had 4 negatives here and only 3 positives, you'd have a current. You'd have electricity flowing. We don't have any electricity flowing at this point. We will see cases where electricity flows, but not just yet. So the charge is constant in series. So to do in series, you use the reciprocal. 1 over the equivalent capacitance is 1 over C1 plus 1 over C2. You have to do it as fractions. It's a little harder. So let's get the equivalent capacitance of this setup. We have it with a 9-volt battery. Those are like the little rectangular batteries that you use in smoke detectors usually. And what we see is these are all in what we call parallel. They don't go, okay, first you go through this one, then you go through that one. When the current comes out here, it could go and branch in various directions. So the equivalent capacitance is really easy. 5 microfarads plus 10 microfarads plus 3 microfarads. By hooking them up this way, we get a bigger equivalent capacitance of 18 microfarads. So that's really good. That gets us more capacitance, more charge we can store. I think you can see these parallel ones are really, really straightforward. Doing the ones that are in series requires a little bit more math. It's a good time to make friends with your parentheses on your calculator. So in this case, they're definitely in series. You'd go for this one, this one, this one, just like you're watching episodes of a TV show. 1 over C1 plus 1 over C2 plus 1 over C3 is our series of capacitors. So now we have to use fractions. I should have mentioned this in the other one, but they're all in microfarads. So that's no problem. Since they're all in microfarads, we can keep them all in microfarads. It won't matter. Here's my secret. I don't worry about getting a common denominator and doing the fractions. I just put them in parentheses in the calculator. I do parentheses 1 divided by 5 in parentheses plus parentheses 1 over 10 plus parentheses 1 over 3. And I get a decimal number, 0.6333 repeating. But don't forget, this is 1 over C equivalent, so we do have to take the reciprocal. And the minus 1 here, 1.58 microfarads. So it's going to depend on whether they're in parallel or series, which one you use. Now let's do another one. And we'll do a two-parter. So we have this setup here with 24 volts, maybe two 12-volt batteries. We have to decide, well, is this in series or parallel? When the electrons come out of here, they have a choice where they can go. There's a branching. You could imagine if this were water, this were like channels of water. The river could go this way, or the river could go that way. So, since that's the case, these are definitely in parallel. And we like the parallel ones. They're easy. Because all we have to do is add up the 2.32, microfarads, plus 1.2 is 3.4 microfarads. Now B says, well, what charge can you put on this setup of capacitors? No problem. We go back to QVC. It's a 24-volt battery. That's a really strong battery. 3.4 microfarads. You might say, why didn't you make that times 10 to the minus 6? It'll be all right. This normally gets us coulombs, but we have the U in there, the microfarad, the mu, and we can just leave it there. So 24 times 4 would be close to 100, so times 3.4, yeah, I'm not even going to calculate it, because I certainly believe that, 81.6 microcoulombs. Now, if I had made this 3.4 times 10 to the minus 6th, let's see what I'd get there. 24 times 3.4 to the minus 6. 8.16 times 10 to the minus 5th regular coulombs. Either would be all right, but it's just easier to leave it as micro, so I think we'll go ahead and do that. And then we'll do some more problems in our next voltage video.